Is disease ecology, mostly studied viral pathogens during my graduate program. I'm just generally interested in modeling phenomenon that is dynamic in nature, and so done a lot of time series analysis during my PhD, and hope to continue that in my current work as well. So I'm going to present this work that I did as some part of my PhD. And it's essentially a case study in trying to use mathematical and statistical models to try and understand how disease dynamics happens, mostly in the phase where you have got this reemergent phenomenon in viral pathogens. I think I should try. Is this connected?
Yeah, I think it timed out. No rush.
Okay. This is 109, right?
Yeah, 109.
All right. So, as I said, this is like a case study of using mathematical and statistical models to try and understand the ecological determinants of Mumps reemergence. So, to motivate this problem a little bit, I want to show some data. It's roughly around in the early 21st century here. So, you see Germany in 2016. England in 2006, we've got China 2009-10, Netherlands is 2010, Canada is around 2010. All these countries have had recurrent resurgence of mumps in the early 21st century. And one salient feature about all these countries is the fact that they have very high vaccine coverage for mumps. It was quite astounding when this started to happen. So just a little primer. Mumps is a disease that's caused due to a viral pathogen of the family called paramyxovirinae. In children, it causes really mild infections with swollen salivary glands and fever. But if you get them as adults, you get severe, infections, and disease outcomes can cause, short-term or long-term sterility in males and females. So it's pretty serious. In the pre-vaccine era, you have quite strong seasonality in these epidemics with these endemic potentials, with around 150,000 cases occurring throughout the world. One more important thing that is relevant to this study is that mumps generally has a high diversity of strains circulating throughout the world with no particular selection pressure, but the two pathogen strains which are most relevant for this particular example are these two genotypes, genotypes A and genotype G. And they'll become relevant in just a moment, but I want us to have that in mind while we are going ahead. So just to recap, yep, go on.
Do you want to wait for questions until the end? Or?
No, we could have this as an interactive session, so we'll jump in there. Go on.
Well, I have a question. Also, severe testicular pain just jumps out of you over there.
Yeah.
So if you were unvaccinated and you had mumps, does that immunize you in the future?
It does, yeah. It causes if you get measles after you get mumps, then it's a different story. But if it is just the mumps infection, then yes, you have a lifetime immunity. Yeah.
So the vaccine that we get, is it specific to any, like A and C, A and G, or is it broad spectrum?
Spoilers.
Okay.
So yeah, that's why it becomes a bit important. The vaccine uses genotype A and has been traditionally using genotype A, and so I'll get to that in just a second.
The other question I have is, like you said, there was high levels of vaccination in these countries. Like, what is the percentage?
Yeah, it's about
herd immunity and stuff like that.
Yeah, so it's definitely about. So it's difficult to say about the herd immunity, because the R0 for this disease is so high. It's not really feasible to vaccinate above herd potential. So generally you have targeted vaccinations. So given targeted vaccinations, you have very high vaccine coverage. So 95% of the groups at risk are vaccinated, and that's why you have herd immunity in the risk-causing groups. So it's generally infants.
And has that changed over time? Like when I went to school, like when they were giving the MMR vaccine, like you just got it.
Mhm.
And I imagine now, like it's probably a shitload of paperwork and people not getting their kids vaccinated.
Yeah, I mean the vaccines are still very regular. Like there's definitely 2 dosages that are to be given.
Mhm.
But generally speaking, whenever you have like international mobilization, like for example, I moved from India to America, I had to get a booster,
Right.
no matter what. So generally, the schedule is for 2 dosages. One is at birth, one is at between 3 to 18 months, and the other one is post 5 years. So those 2 dosages are still in place.
Okay. So even in the US, people are getting their kids vaccinated.
That's right. Yep. So, thanks for beating to the punch.
Sorry.
That's all right. So, I mean, naturally, there has been suspicion about how well these vaccines are, and most of this investigation that I'm going to present today is about trying to understand what kind of vaccine imperfection might be resulting in these reemergent dynamics that you see in the population. So, 2 very popular studies that came out at the same time, 2018, very ironically talk about 2 different things about vaccine imperfection. So, on the left, so Lunard and Grad sort of did a meta-analysis of trying to understand how vaccine trials, which were conducted at different times since the vaccine dose, change your relative risk of getting mumps infection. And you can see that there is an upward trend in this relative risk. That means as you kind of move away from your time of your first vaccination, the chances of you getting mumps sort of increase as a cohort, as within a population. But at the same time, Goma kind of this group had a slightly different idea. They find these antigenic differences between the 2 strains that are currently under question. So the strain that was used in the vaccine, which is genotype A, and the strain that is commonly circulating in the late 21st century, which is genotype G. So there has been a massive turnover of the genotypes, and you find antigenic differences between the 2 strains. So there has been this conjecture that, well, it may not be vaccine waning of vaccine imperfection, but the fact that there is a mismatch between the circulating strain and the strain that is used in the vaccine that renders the vaccine imperfect against protection for infection, and that's what's causing these sudden epidemics. So before I go forward with the analysis and how I kind of try to tackle this problem, as I said, the main objective was to try and understand whether I can find signature of these mechanisms of vaccine imperfections within time series. So it's a very broad stroke account keeping basically. But I'm going to go over the data. So as I said, vaccine licensure in America, so this is a case study for America only, happened in 1967, after which you have a very high vaccine coverage quite early on. Due to that, you kind of see this precipitous drop of mumps incidence right after the vaccine rollout, causing around 99% of reduction. Following which there was the first resurgence of mumps, as it is called, in 1989, which caused the instating of a booster dose, which is like the second dose, which is now given at 5 years, which causes a further decline. Following which you kind of start seeing these epidemics from 2006 onwards, and then ongoing transmissions. So this is so most of my analysis is sort of based about the epidemics that are quite recent. The other type of data that I have for this, that I've used in this analysis, is that these cases are age stratified, and then there is this turquoise colored unstratified group which we did not find age for, so we had to kind of account for that within the observation model. One thing that to note is that there is the dominant age group of cases in the first resurgence is sort of the younger age class, so 5 to 15-year-olds. But in the most recent epidemics, you have an inflation of this older age class coming into play. So there is a shift in the age distribution of the cases that were recorded from the first resurgence. to now, until now. As I said, this thing comes into play that there has been a turnover of the genotype that have been circulating around, which was A initially, and that is why A was used for the vaccine production, and now it's all G. All right. So for the people who are from like the engineering and physics background, hidden state processes are pretty much quite common, and these are generally used in disease modeling or ecological modeling of phenomenon. And most of us are kind of aware of what these are. You take a population of individuals and you kind of categorize them into these conveniently structured, susceptible, exposed, infectious, and recovered individuals. And because I've got an age-structured population, you've got age classes. So you kind of have these two dimensions that you have to kind of think about. And all of these are coded as different hypotheses for the mechanistic implications, which are coded for the vaccine imperfections. So I'm going to go over these models real quick. There's this basic no-loss model just to have like some sort of a benchmark where if you get the vaccine, so you've got the natural history model here, which is susceptible to exposed, infectious, and recovered. And then you get the vaccine, and the no-loss model says that if you get the vaccine, you're immune, you're completely safe. So this is like and I don't like to call it the null model because this isn't it, but this is like a benchmark to say if the vaccine works perfectly, you should see some sort of dynamics, and what happens if you were to make this vaccine perfect in some. The next one is a vaccine. So I've got a vaccine model, but now I've got a vaccine with a finite duration immunity associated with it, following which you get this rate at which you kind of become susceptible again, and you're kind of equally likely to get infected as you were if you were completely susceptible.
And your variable there is just your exponential decay?
Currently, yes. But thanks for bringing that up.
Sorry.
No, it's all right.
I didn't read your thesis, trust
Right.
me.
I mean, it's so you want to play around with the definition of how you want this immunity to decay. So one easy, like the most straightforward way which you can use, change the distribution from an exponential to a more, uniform looking or peaked looking distribution is using this chain rule where you kind of distribute your residence time between multiple classes, thereby causing a little bit of a delay, and then you kind of have this, a gamma or an Erlang distribution for your residence time within the. So we also have played around with the shape of
Is that years on the bottom?
This is just a pictographic to like kind of demonstrate what happens if you move from having just one vaccinated compartment to 3 vaccinated subcompartments. You kind of move from having an exponential curve to a more, a distributed. So what you're really doing is you're trying to inflate the variance on your distribution and ask the question, what happens there? So you're playing around with the idea of structure within DNA. And then finally you have a structurally different model where you have got 2 circulating strains. And you're essentially, now you're trying to say that the vaccine works perfectly if you were exposed to genotype A, but if you were exposed to genotype G, then there is a non-zero imperfection, which is that parameter epsilon. And that is the degree to which your vaccine is leaky against this, this novel strain that is going on. All right.
So why would your sigma and gamma and stuff like that be the same on both sides if you're modeling different strains?
That's a pragmatic decision that I went ahead with. So it's, it does not happen.
Just part of the structure.
Yes, and also it's because more importantly, the data that I'm dealing with is age-structured cases of mumps. We do not know how many of those cases are related to genotype A versus genotype B. So there isn't really signature associated with having multiple strains. I'm just trying to test it in terms of, I'll show you what. Like, there's a dynamic signature which is different between the 2 types of mumps. All right. So this is just, before I start fitting these models, it's easier to do them when you start, you have some realism into the model. So one of the things that you kind of have to keep track of when you're dealing with age structure is that you also want to know how these age structured populations come in contact with one another, because one of the most important thing about diseases is that diseases spread as a condition of contact, which is generally taken as a single parameter, but when you have these stratified populations, you also have to account for how one age class comes in contact with the other age class. So that matrix right there is the matrix of contact rates between these different age classes. The other things are demographic characteristics about this population, just to make sure that we are modeling America, for example. So the things that I have are like birth rates, I've got age-structured populations, and then I also have like these inferred migration rates, which are basically accounts.
So when you're doing these studies, is the data anonymized?
Yes, for sure. Yeah, because otherwise it would be unethical. I mean, when you say anonymized, you mean like I do not know what.
So he works for a health insurer. We work for health, so we have more personal level data, but he's got giant scale data.
Yeah, like
this is
giant reportable diseases.
Interesting.
He's got small amounts of information on each case.
Yeah. I do not know who this who person X was.
Okay.
Who has been recorded as like.
Huh.
Yeah.
In my mind, that makes it a lot harder, because I know who the paid members are.
Mm-hmm.
I'm able to pull in a ton of kind of like first party organic data and then purchase data.
Right.
Yeah, but you're
You
not,
know?
there's no world in the US where you're gonna have data where you actually know all of the contacts, right? You actually
True.
know a whole population.
True,
It's always a weird population.
And
So, yeah, we say that, but
Well,
then
was that
Experian
question
and the
like-
credit agencies have information on every single eligible American with a address.
Right. So now where I work, I'm kind of more careful about making these broad stroke assumptions. So I'm currently using these contact matrices which have been published in like a few of the the classical articles where they did a lot of diary records and tried to estimate what may be the contact rates between different socio-demographic variables. So one of them is rich and poor. So what is the contact rate between different degrees of richness and poverty? And one of the other ones, which is quite classically used in disease modeling, is age structure, where you're trying to understand, children come in contact with their parents more often than they do with, or when I say children, I mean infants come in contact with their parents more often than they come in contact with like other infants. So that's how they kind of configure these contact matrices. So these are diary surveys basically. There's population structure. There is some information about vaccine coverage within the population. So there are these two dosages. So this is the neonatal dose, 3 to 18 months, and then there's a 5 to 15-year-old. So but as you become 5 years, you kind of get that dose. The problem is, and this is something that I had to kind of work through, is most of the data is like within the recent time period. And the problem was also about trying to understand how imperfect this vaccine is. So now there are two unknowns and there's a single equation. And so I had to make assumption about one because I was interested in the, trying to understand how imperfect the vaccine was. So this blue region that you can see here, it had to be imputed or was treated as a sub-hypothesis while trying to fit models to data. Like there isn't another way to go and understand. Like because there is no way of simultaneously understanding how the vaccine coverage kind of reached a certain level and ask the question how imperfect the vaccine was, because they kind of are at odds with one another.
Did you treat it like a hyperparameter or hypermodel?
Yeah, it's a hyper. It might be
hypermodel
right,
to make up a word.
Exactly.
Gotcha.
All right. So we spoke about the hidden process, and now we're in this region of something called as the partially observed Markov process. I think there might be some people who know this, but just so that we are kind of all on the same page. The models that I was describing before are essentially described as differential equations. which is down here. This is the hidden state process, which is independent of anything else other than the time step before, which is like the which is shown in this X and the initial conditions, of course. But what is observed is like some sort of an impure manifestation of this hidden state, which is generally, in my case, it is cases. In some other, there's an emergent property which goes through this idea of an observation process. In regression, we call it unexplained error, like the linear regressions are unexplained error. In my case, it's a slightly complicated likelihood function, which I essentially then use as my objective. So to construct it from first principles, we kind of have this idea of, the idea of probability. What is the probability of this data that we are seeing given certain model, right? So there are two parts of this likelihood function. So there is one which is age structured, and the other one which is not, right? And the way you can kind of account for this is you use the probability that an age was recorded, and we know that from like the proportion of the cases that were age stratified versus the proportion that were not. So you have that eta that just comes out from the data. So you can essentially discretify, you can stratify your observation as the part of the data that was age structured and then the part of the data that was not. Then you take the product of the whole thing, and then you do that for all age classes, all times, and that becomes your likelihood function. And likelihood function is nothing but a way of trying to assess how well your predictions, which are shown in red, fit your observations, which are shown in black. It's a degree of goodness of fit, described in a probabilistic way. I wanted to say something about this other than that. I think I've kind of went over it, didn't I?
And you had all these probabilities, or did you?
So those are the probabilities that you kind of assess, because I've got data, and I've got some parameters that go in through an optimizer or some sort of a grid search method, and you assess this likelihood function at every one of them, and then you kind of build your likelihood profile across different parameters.
So the only variable you have there is D, and then the rest you're trying to determine. You're minimizing your likelihood.
That's right, because I've got D. Yes, that's right. So this is simulation. Eta is a covariate that goes in because I know the proportion of the data that is age structured versus the data that isn't. And rho is just a degree of underreporting, which is something that generally happens with incidence data because you are less likely to report your disease than you are over-reported or reported. So there is a non-zero probability that the observed case is a subset of a bigger number of cases that are.
So the only thing you don't know is C.
That's right. But C is a manifestation of your simulating the model.
That's what you're solving for.
So that's basically what I just said. Oh yeah, and then currently I'm assuming that this is all a random draw from an over-dispersed normal model. Again, this was why is it a normal model? Because normal Gaussians perform well. And I wanted to, it's a bad, no, if it was me, the me from now, back then, I would have thought about it a slightly different way. But anyway, for accommodating variation within the observed process, I do account for it using over dispersion in this normal model. So you kind of I tried to give it a feel for a negative binomial, which is what is better for systems like these. But at large numbers, it kind of all washes away. Normal distribution is not the worst thing. But anyway, sorry, I'm going to move on. I'm already 20 minutes. That's fine. So that was the whole setup for how the model was set up and what the objective function was. I'm now going to talk about the results of the paper that I have and some implications that come out of it. Again, a quick recap before we move into it. the question is what kind of vaccine imperfections, if there is vaccine imperfection, might be the most plausible explanation behind the emergence of mumps epidemics in the recent era. Alright, so I'm going to show you the results of my model fits. The columns are all of the models. I'm only showing 2 waning models. There were multiple waning models. And the best leaky model, there were multiple leaky models because the introduction time and the age classes where you want to introduce the second strain is kind of a combinatorics problem, and I had to kind of go through all of those possible things. So I'm kind of washing all over it. These are the best 4 models that I'm kind of using for the analysis. And the rows are the age classes, just so that. And as I had said, the purple is the no loss model, which is going to be like our benchmark. So as you can see, if the vaccine worked perfectly, so the data is currently shown in the solid black lines, and the bands show the prediction from the model, the 95% prediction intervals of the model. If the vaccine worked perfectly, you see that there are way too many cases in the system than what you will observe, which is shown in the black line. So now these are the other models that I had. Among all of these models, statistically speaking, waning with an exponential is enough to explain the variation within the data as best as it can. Right. Having said, the waning model with like an Erlang, which is like 3 subclasses, also does a good job. What it kind of does is it sort of starts lifting these up quite rapidly later on, and it does not capture the decay that you kind of see in the late or the most recent times. So that's why it may be suffering. So among all of these models, waning model performs the best.
How do you get an AIC of 0?
Oh, that's a delta AIC. So it's the difference from the minimum AIC.
And that's the number.
Okay.
That's right. So it's easier to compare because I can have numbers which are in like 10,000s, but it's easier to see 0 versus 20. Alright, let's really quickly look at the parameter values. So I'm not sure how, I think since pandemic we all know what R0 is, but as a refresher, R0 is the average number of secondary cases